Welcome back, everyone. So what we're going to be talking about now is the mass of the Milky Way. We want to know how to measure how massive it is, and we obviously can't just pop it on a set of scales. So what we're going to do now is we're actually going to go through how we actually work out how massive the galaxy is.
Yeah, I'd love to see the scales that the Milky Way would fit on. We can cut that out.
That was a bad joke.
Yeah.
I'm not cutting it out.
One of the benefits here is that we know that we can measure individual stars in the galaxy, and also that these stars more or less orbit on circular orbits. You know, everything's not perfectly circular, but it's not too far off. You know, for any individual star, it's not a perfect approximation, but for enough stars averaged over many of them, it is. Because things are orbiting in the galaxy, there's the only force that's acting on them is the centripetal force of them going around. The force that are acting on them are the gravitational forces from all the other objects. And this manifests as a centripetal force. The good news is there's some tricks about gravity that you might have seen before that help us out a little bit. Let's talk through what that looks like and how we can actually use that to measure masses in the galaxy. Unfortunately, I'm left-handed, so let's swap sides. Not I'm unfortunately left-handed. It's left-handed, it's cool. If you're left-handed, good job. So we know that under the approximation of there's only two bodies, which there's more than two bodies in the solar system in the galaxy. But just for a moment here, we know that the force of gravity is big G, Newton's constant, the same one we've seen all term, times m, the two masses of your two objects, divided by r squared, our old friend the inverse square law. And that this is then equal to centrifugal force if you have a circular orbit, mv squared over r. Done. Now, in practice, this is the force for any two objects, and for many, many objects, like a galaxy full of objects, we would sum over every m in here. But there's a trick when you're dealing with spheres, and it's not the worst approximation of the galaxy as at least a slice of a sphere. That we can treat everything interior to your object as if it was a point source at the center, and everything exterior as if it doesn't count. Because of the way the integral works when you sum over, you have a lot of things that are really close to you on the far side, and more things that are further away on the other side, outside of your sphere, and those end up canceling out.
What Ben's basically saying is if you were to have a sphere like this, for example, and you were trying to work out, the mass, within an orbit, however far from the center, so for the galaxy where you have stars everywhere in here, you're looking at the mass of everything in here. Or if you were taking the orbit out here, you would look at the mass of everything in here, and everything outside doesn't matter.
This is something you might have seen in other inverse square law applications, such as like in electrostatics, in your first year physics course. You might see that you can integrate over everything interior, neglect everything exterior. We'll talk about this similarly in stellar physics as well. Same thing works for gravity inside of the sun. So this means for us, we can treat everything inside our point of the galaxy as being at the center and treat it as a single object. And so now this two-body law applies. Masses cancel. Gravitational force never depends. Gravitational acceleration doesn't depend on yourself. Masses often cancel on these types of things. R is non-zero, so one R also cancels. And then we have G, M. I'll put a subscript of M enclosed, but I'll also spell it correctly, M enclosed. Divided by r, your distance, is equal to v squared. Now, m enclosed is the thing we care about, how much mass is inside of us in the galaxy. Big G is a constant that we know really well. R is our distance. We know how to measure where we are in the galaxy through things like parallax and Cepheid variables. And v is how fast things are moving. We can measure the velocities of objects through their proper motion and their Doppler shift. And so we can measure everything here except the mass enclosed. So rearranging, v is equal to, that's not the math we care about. We're trying to measure the mass enclosed. M is equal to g times v squared over r. And we can do a little dimensional analysis, verify that's correct, leave that as
Which it is not. You've rearranged this completely wrong.
Perfect. That's why we do dimensional analysis, to check this out. Remember, students, it's important to get a good night's sleep before you do some math. We are looking for m, which is v squared times r over g. That seems better.
So I guess one thing to leave us off with is you might be thinking, okay, so we can measure the velocity of stars around the center of the galaxy, and we can work out the mass enclosed, but the question then becomes, what does this relationship look like? Do these velocities of stars, are they what we expect them to be? Do these stars follow Keplerian orbits? As you get further and further away from the center of the galaxy, do the stars orbit slower and slower?
Right, and this is something that we should in principle work out because we know the masses of stars and we know where they are in the galaxy. And so we should be able to make a pretty good theoretical estimate of what this mass looks like and what this velocity then should be at a given radius that we can measure for a constant g. And then we can see, does that hold out? Do we measure the right mass and velocity that we expect, or is there something else going on in the galaxy?
This was something that was discovered that was quite shocking, actually, that even though we expected the velocity of stars orbiting the center to be slower and slower, we found that it actually leveled off, that they were traveling quite constant, as if the Milky Way were rotating as just like a solid disk. It wasn't winding up on itself. They were orbiting at the same speed. Which that means that the velocity keeps being faster than you expect. There has to be more and more mass than you'd expect. And so there's some extra mass that isn't being accounted for when you just look at stars. Yeah, and that's the important thing, that it is mass that you can't see, because we can estimate pretty accurately the mass that we can see, but we have extra mass that we can't see. And this was, I guess, one of the triggers for dark matter, which we will talk about more later on in the course.
Yeah, wonderful. So thanks for listening, and we'll see you next time.
See you there.